Hello students, welcome to this lecture on the subject of Advanced Semiconductor Devices KEC 056. This is lecture number 7 and I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. In this lecture, we are going to continue our discussion from the previous two lectures on the topic of carrier transport. So, this is part 3 of this topic. In the last lecture, we had started the concept of how charge carriers move inside a semiconducting crystal. We had identified that semiconductors tend to be bipolar in nature, which means carrier conduction can be because of two types of charge carriers, namely electrons and holes. And these both charge carriers are complementary to each other in terms of their charge carrying capacity or direction of movement. Okay. And we also identified that in any semiconductor at any given point of time, you can have up to two different mechanisms of current or charge carrier transport. These are known as drift and diffusion current. So, the total current inside a semiconductor is composed of drift as well as diffusion, and drift can be produced by both electrons and holes in the presence of an external electric field. Diffusion can also be produced by both electrons and holes in the presence of a carrier concentration gradient. Okay. And we also discussed the topics like conductivity, resistivity and mobility. Now, we want to proceed further and see some different cases and applications of how this phenomena of charge carrier transport can be used for different purposes. Okay. So, first topic which we are going to discuss today is known as Hall effect. Right. So, Hall effect, if you see this figure shown on your screen, you will see a bar of semiconductor. Okay. It is a 3-dimensional view which has been shown for this semiconducting material. It has two surfaces, surface 1 on the bottom and surface 2 on the top. These surfaces are separated by a thickness d, okay, and there is a width w. Okay. So, these are the dimensions of it. This semiconducting crystal is under the influence of an external magnetic field, okay, B, right, and current I has been applied to it, and we are going to see what is the effect on such a situation where a semiconducting material has been kept inside a magnetic field and a current has been applied in such a way that both current and magnetic field, their direction is perpendicular to each other. Okay. So, this is the setup which is used for understanding and seeing the application of Hall effect. From the purpose point of view, Hall effect is used very commonly to measure very critical parameters of any semiconductor. These critical parameters are carrier concentration, how many charge carriers, whether it is electrons or holes, how many charge carriers are present per unit volume, what is the carrier mobility, okay, and what is the type of this semiconductor, type or polarity, basically whether your semiconductor is N type or whether the semiconductor is P type. So, these are the parameters which are used to obtain, or these are the parameters which are actually obtained from analyzing a material in this kind of an arrangement or Hall arrangement. Okay. So, when a semiconductor which is carrying a current I, okay, so the direction of current is in the x, so I is in the x direction. Okay. If such a material is placed inside a magnetic field B, whose magnitude is B or intensity of magnetic field is B, such that both I and B are transverse to each other. So, B is in the z direction. Okay. In such a case, it is known that an electric field E is induced in the direction which is perpendicular to both I and B. So, an electric field will be induced in the direction y. Okay. So, in this 3-dimensional arrangement, you can see that current I is flowing across the x direction, magnetic field is applied across the z direction, and an electric field is induced in the y direction. Okay. So, all these parameters are transverse or perpendicular to each other, and this inducing of electric field, this phenomena of electric field induction is known as Hall effect. Okay. So, this is your circuit arrangement and this is the phenomena, this is the definition of Hall effect, right. So, a current carrying semiconductor placed inside a magnetic field experiences a perpendicular electric field, right. This is Hall effect. How do we use it? See, if I, as I said in the previous slide, if I current is in the positive x direction and B is in the positive z direction, the charge carriers will experience a force in the negative y direction. Okay. Now, this current can be because of both electrons as well as holes. Okay. So, if your semiconductor is n type, the current which is flowing is predominantly going to be because of electrons. If your semiconductor is p type, the current predominantly is going to be because of holes, right. This we already know from the doping concepts and from previous subjects which you may have studied. The current, if it is due to holes which are moving from left to right. Okay. So, if holes they are moving, if the direction of holes is left to right, the direction of the hole current will also be same. Okay. So, this will be the direction. Okay. If it is p type, if it is n type, you will have electrons which will be flowing from right to left. Okay. We know that holes and electrons are always flowing in opposite direction and the flow of electrons is always opposite to the direction of current. So, we have said initially that current, if it is in the positive x direction, electrons will tend to flow from right to left, right. So, the current may be due to holes moving from left to right or electrons moving from right to left. So, irrespective of the polarity, whether your semiconductor is n type or whether it is p type, charge carriers are forced to move downwards towards region 1. Okay. So, the direction of electric field is in this direction. This is your electric field direction. This is the direction of current and this is your magnetic field. Okay. So, irrespective of this, of the nature of your semiconductor, whether you have an n type or p type, your charge carriers, whether electrons or holes, are moved towards the downside minus y axis. Okay. So, how this is useful? Now, if the semiconductor is n type, so current predominantly carried by electrons, these electrons will accumulate on side 1, this surface, this lower surface which I have shown here, this is surface 1. Okay. And this top surface, this is surface 2, okay, separated by a thickness d, right. So, this is region 2 and this is your region 1, the lower side region. Okay. If the semiconductor is n type, so when electrons get pulled towards surface 1 downwards, this region gains electrons. Okay. So, say initially in the middle you have charge carriers flowing, electrons flowing from right to left because current is from left to right. These electrons get pulled towards surface 1 below. Okay. So, surface 2 effectively becomes positively charged as compared to surface 1, or I can say that this region 1 is more negative as compared to region 2. A simple polarity test, right, a simple measure of voltage across it will tell you that on which side the needle moves and you would know that which side is more positive and which side is more negative. So, if region 1 is more negative, it must have been an n type semiconductor. Okay. So, if you do not know the polarity of this semiconductor, if you do not know the type of this semiconductor, if region 1 is more negative as compared to region 2, the semiconductor is n type. Opposite, contrary to this, if your semiconductor was p type, region 1 will have more accumulation of holes as compared to region 2. So, holes moving from left to right will get pulled downwards towards region 1. Okay. So, a simple polarity test will tell you that region 1 is more positive as compared to region 2. What this shows is that in this kind of an arrangement, if region 1 is more positive, it is a p type semiconductor. Okay. So, the region, the voltage which develops, it is measured across region 1 and 2, right. So, if you measure this voltage across these two regions via a voltmeter, this is known as Hall voltage. If Hall voltage is positive, it is a p type semiconductor. If it is negative, it is a N type semiconductor. Okay. So, this is how you use Hall effect arrangement to measure the polarity or identify the type of your semiconductor. Apart from that, you can use it for measuring carrier concentration. Okay. Now, you see the charge carriers in this arrangement are experiencing two types of forces. One force is applied via this magnetic field, okay, and we know that magnetic field exerts a force only when your charge carriers are moving. Okay. So, this force due to magnetic field is given by whatever force is exerted by this magnetic field on a moving charge carriers. Here Q is charge, B is the intensity of magnetic field and Vd is your drift velocity. Okay. We have already discussed drift velocity in our previous two lectures. This force and the current carrying capability of this semiconductor results in an electric field induction. So, a second force is exerted which is due to this electric field, which is, and we know electric field is force per unit charge. So, this force because of electric field is equal to Q times E. These forces balance each other. Okay. So, you can say that Q dot E is equal to Q dot B dot Vd. Okay. I have already defined the symbol. Q is charge, E is electric field intensity, B is magnetic field intensity and Vd is drift velocity. Okay. And if d is the distance, as I have said that the thickness between these two regions or the thickness of this material is actually is known as d. Okay. That is the symbol for that. So, if the distance is between these two region is d and the voltage across these two region is Vh Hall voltage, electric field being the voltage gradient, I can say that this induced electric field is equal to Vh over d. Okay. And this Vh is equal to E dot d, right, and E is equal to B dot Vd, right. So, the two forces, one due to magnetic field, another due to electric field, they balance each other. So, they are equal to each other, right. So, we can write electric field force due to electric field equal to force due to magnetic field, Q gets cancelled. So, E is equal to B dot Vd. We know that Hall voltage is E dot d, right. So, combining these two equation 1 and 2, you get equation number 3, which says that your Hall voltage is dependent upon magnetic field intensity, drift velocity and the width of the or the thickness of the semiconductor. Okay. And drift current density, we have derived the expression in the previous lecture. J is equal to NQ mu E or J is equal to sigma E basically. Okay. This can also be written as rho dot Vd, where rho is nothing but charge density. Okay. So, charge density rho is defined as N dot Q. This is known as charge density, coulomb per cubic centimeter. Okay. N is the carrier concentration, Q is the charge. So, total charge density is N dot Q, right. Current density is also defined as current per unit area. If I is the current flowing and area is width times thickness. So, I can say that this rho dot Vd, which is my drift current density, is equal to current per unit area. Okay. Simple explanation, we already know the expression for drift current density, N Q mu E, N is carrier concentration, Q is charge, mu is mobility, E is electric field. Okay. N dot Q is the definition for charge density rho, mu E is the expression for drift velocity. Drift velocity proportional to electric field, proportionality constant being mobility. Okay. We have already seen this in one of our previous lectures. Okay. So, now equation 3 can be written as Hall voltage equal to B dot d, Vd gets replaced by J over rho and J is I over W d. Okay. So, this is my expression for the Hall voltage, right. So, you can see that Hall voltage depends upon what? It depends upon magnetic field intensity which has been applied, current I which is flowing through the semiconductor and the charge density in the semiconductor and the width. Okay. So, this is what. So, if I am able to measure these parameters, okay, so if I know VH, if I apply a connect a voltmeter across region 1 and 2. So, I measure Hall voltage. Okay. I know how much magnetic field is applied, how much current is flowing, I know the physical dimension. From this I can calculate rho. Okay. So, this I can use rho I can calculate as V dot I divided by V h dot W. So, this calculation gives me the charge density, and if I know charge density I can calculate the carrier concentration. Okay. So, with this I can calculate the carrier concentration. Okay. So, the applicable to both n type and p type semiconductors. Okay. So, if you have a p type semiconductor you will replace p here. Okay. Apart from this you can use the same equation for measuring mobility. For mobility we define what is known as Hall coefficient. Okay. Hall coefficient is nothing but the reciprocal of charge density 1 by rho. Okay. So, RH Hall coefficient is defined as 1 by rho. This is the equation from our previous slide, Hall voltage equal to B dot I divided by rho into W. Using these two equations, I know that Hall coefficient is reciprocal of charge density. So, I can write the equation for Hall coefficient as Hall voltage times W divided by D dot I. Okay. Conductivity is known as NQ mu, sigma is equal to NQ mu, N dot Q is charge density, rho dot mu, which basically tells me that mu is equal to sigma dot RH. Okay. And what is RH? 1 by rho. Right. So, measurement of this charge density is basically useful in calculating carrier concentration as well as it is useful for measuring mobility. One should remember that the value of RH, since it is dependent upon charge density, charge is negative for electrons and positive for holes. So, your Hall coefficient is going to be positive for holes and negative for electrons. Okay. So, this way we have used Hall effect for measuring parameters like carrier concentration, mobility, okay, and type of the semiconductor. So, this is the topic of Hall effect. Moving further, we are going to study what happens when you apply a very high intensity of electric field in a semiconductor. Till now we have seen that drift velocity is directly proportional to electric field, and this drift velocity, the constant of proportionality is mobility. Okay. So, for electrons you use electron mobility, for holes you use hole mobility. Okay. At low electric fields we can easily say that this drift velocity is directly proportional to E. This is only valid at low to moderate values of E. When E starts to increase, you start to see more collisions and scattering inside a semiconductor. Okay. In that case, mobility is no longer field independent, it starts to depend upon electric field value. So, at high values of electric field, drift velocity does not rise with electric field and it approaches a sort of a saturation. Okay. So, if we try to plot a graph with electric field and drift velocity, initially it will be proportional and then it will try to saturate. And in very extreme cases, it might also at very high electric fields, it might also start to roll off a little bit. Okay. This predominantly happens why? Because at high electric field, so this is the graph basically which shows electric field is on the x axis and drift velocity is on the y axis. So, you can see initially for most of the semiconductors, say for silicon, initially drift velocity increases and then it becomes constant. For compound semiconductors like gallium arsenide, it becomes constant and also starts to roll off. Okay. So, we can say that this direct relationship between drift velocity and electric field is no longer valid at high values of field, right. Why this happens? When electric field increases, the average energy of charge carriers also increases. So, you are applying extra energy when you are increasing the magnitude of electric field, you are providing extra energy to your charge carriers, right. when you provide extra energy to charge carriers, that energy has to be compensated somewhere. So, either charge carriers start to move around, they start to travel fast, and then the chances of collision also starts to increase. Now, in addition to these charge carriers, this energy, extra energy which you are supplying in the form of electric field may also gets transferred to the stationary ions and atoms. These atoms start to vibrate, they can't move, which is known as a phonon. Okay. So, when the average energy of charge carriers increase, they also acquire a higher temperature or a higher effective temperature, which is higher than the lattice temperature, or you can also say the ambient temperature of the crystal. Okay. So, this effective temperature of charge carrier is higher than the lattice temperature, and this temperature, effective temperature, keeps on increasing. This difference keeps on increasing when you apply higher electric field. Okay. So, this results in increased phonon scattering, and we have seen in our previous one or two lectures that whenever there is high phonon scattering, right, there is a tendency for mobility to fall off. Mobility is temperature dependent. Initially it increases and then it starts to fall off. Initially it increases because of things like impurity scattering or lattice impurity scattering, and then at higher temperature it starts to fall off due to phonon scattering. Okay. So, your effective value of drift velocity is equal to mu naught E, where mu naught E is your mobility at low to moderate values of electric field. Okay. So, you can call it low field mobility, multiplied by the square root of T over T E. At reasonable values of electric field, these values are nearly equal. So, then your initial direct relationship between velocity and electric field is valid. Okay. But at high values of field, where effective temperature increases, this term becomes lower than 1. So, your drift velocity starts to either become constant or in extreme cases starts to fall off, right. And this is the ratio of this effective temperature to lattice temperature, and here C subscript S is nothing but velocity of sound, E is applied electric field. Okay. So, this is the effect on mobility and drift of charge carriers when there is very high value of electric field is applied, right. So, this graph also tells you when temperature tends to increase. So, your x axis is temperature, your value of saturation velocity, that velocity which is supposed to be becoming constant, okay, at high fields, that also starts to roll off. So, for silicon the roll off is slightly lower, and for compound semiconductor like gallium arsenide this roll off is quite steep. Okay. So, this is the effect of increasing temperature or increasing electric field on the drift of charge carriers. Okay. And when the electric field is increased above a certain value, your carriers gain enough energy. So, you can have certain electrons and they collide with another atom and they can knock off another electron. This is another high speed electron, this can hit another atom and knock off another electron. So, this phenomena is known as impact ionization. Okay. This multiplication process is characterized by an ionization rate which is alpha, can be defined for both electrons as well as holes. So, one electron can generate another electron leaving behind a hole. So, one high energy electron generates one electron hole pair and another high energy electron keeps on further generating different electron hole pairs. Okay. Next, last topic for this lecture, which is another non-linear effect, is what is known as a space charge effect. We know that the depletion region across the junction in a p-n junction is known as space charge region also, which is composed of ions and depleted of free charge carriers. This space charge in a semiconductor is determined by the doping concentration on either side and the free charge carrier concentration. Okay. So, rho charge density is positive charges, positive holes, positive donor ions minus negative holes and negative acceptor ions. In the neutral region, okay, you would say that your majority charge carrier electrons is equal to doping pentavalent doping concentration Nd, Nd is donor ion concentration and A is acceptor ion concentration. Okay. So, the space charge density is effectively 0. In the region very close to the junction, this may not be the case, okay, for especially for the junction formed by different materials. Dopant types or doping concentration could be smaller or larger than this. The carrier concentration N or P could either be lower or higher than the doping concentration. So, N may not be equal to N D, it may be higher or lower, P may not be equal to N A, it may be higher or lower. Okay. So, in the so called depletion approximation, we say that N and P are assumed to be 0 inside the space charge region, okay, and the space charge is equal to the majority carrier doping level. Okay. Donor ions on the N side and acceptor ions on the P side. But when bias is applied, the carrier concentrations N and P can be increased beyond their values in equilibrium. When this injected charge or injected concentration is larger than the equilibrium value as well as the doping concentration, we say that the space charge effect occurs. So, if we apply a very extreme bias across a semiconductor, the values of carrier concentration N and P significantly deviates from its equilibrium value as well as the doping values. Okay. So, these injected carriers basically control your space charge and the electric field profile across the junction, and this results in a feedback mechanism where field drives the current, which in turn sets up another field which opposes it. Okay. And this space charge effect is more common in lightly doped materials, and it can occur outside the depletion region as well. Okay. So, with this you can refer to some of these references for this today's lecture. So, we come to the end of this lecture. So, we have discussed 3 different topics related to the concept of carrier transport, one being Hall effect to measure semiconductor parameters, another what happens to charge carriers when very high electric field is applied, and thirdly we have studied the space charge effect. So, okay. So, we will continue our discussion of carrier transport in the next lecture. So, thank you for